second episode of the Climate Breakdown. We're here talking about Southern African climate today with Dr Neil Hart. He's a lecturer and researcher at the Department of Geography and Environment, and he's a tutor here also at Christchurch College. Welcome to the second episode.
Thank you for having me.
Let's just start with an introduction to climate in Southern Africa. What can you tell me about a typical, or what you'd expect the climate to look like in pre-industrial levels?
So African climate is a fascinating place. There's records from lake beds, tree rings, other sorts of paleo records that go back quite a long time. That shows that the Southern African climate has varied substantially over the last 10,000 years and longer. Sort of, if we talk pre-industrial climate, we're probably talking maybe the last 500 years, the types of climate that the region has had. And even then, it's been quite a varied climate. So it's one of the parts of the world which has quite highly variable climate. The reasons for this is that it's quite sensitive to changes in global ocean temperatures from the Pacific Ocean, the local Indian Ocean, and to a less extent the Atlantic Ocean. And these have driven some quite large-scale changes in that climate through time, including, for example, in the fact that in the 1920s there was a period when Lake Malawi's lake level dropped so low that there was no water flowing out into the Shira River, and this, that lack of water in that river was something that was subsequent to Livingstone's first exploration through the lower Shira River in the 1850s.
And Malawi's an area of interest that I'll talk to you about in a moment, about tea production there potentially is suffering. So typically, what would be the average? What would you say the average climate would be in a place like South Africa? Is it temperate?
So I mean, Southern Africa is a really big area. We call it the subcontinent. So Africa is the continent, but it's a subcontinent. And across the whole region, there's actually some very sharp gradients. So in the far north, you have the Congo rainforest, or the southern edge. And as you move south, you actually come up onto something called the Katanga Plateau. So this is where all of Zambia's copper mines are. And that's actually quite dry during the winter, and then has quite a wet, rainy season through the summer months. And then as you come further south, as you move down towards the east, so the Indian Ocean, that whole side of the continent is actually quite wet, quite a lot of rainfall, up to sort of 2 meters of rain down that western side of the continent. So the eastern side, east and west, get these right. But if you look at the western side, you have the colder ocean and much more desert-like conditions all the way from Namibia through into South Africa and across into Botswana. So there's sort of a sharp gradient as you move into the tropics and into the Congo rainforest, with the rainfall increasing and there being more forested lands. And then east to west, you're moving from dry on the west Namibian coast to quite wet conditions, the Mozambican coast.
Brilliant. So that was pre-industrial levels. Now if we speed up time and we go closer to today, when we're about 1 degree above pre-industrial levels, what can we say about South African climate as it currently stands?
So it comes down to what you're looking at. And so if you're focusing on temperature, you'll note that there's been some really remarkable changes in the risk of long hot spells, and it also depends where on the continent you are, and if you focus on rainfall, it can be quite varied. What we can say is that in the observed record, really there's a hot spot for warming right about in the middle of Botswana, and this Southern Africa becomes quite an interesting place to study change, both that's occurred in the last century and change as projected to occur, because in a number of parts of Southern Africa, Botswana being one, the change that we've observed until now continues to be the change that models are projecting into the future.
And is it normal to have, throughout the year, is it normal to have periods of intense rainfall?
Yeah, so Southern Africa typically, except for the far southwest, so the area around Cape Town, it typically has quite a long dry season. So from about March or April, the rains tend to move north across the continent. And so from about April all the way till September or October, it's dry. And it can get quite cool, but then by September, October, it starts to get really warm as the sun is coming back overhead. And then the rains start in full force in November, December, and in January and February after.
So that's the rainy season.
Yeah.
Okay, and then how can that influence, or previously, how's that influenced things like agriculture? So what
well, it means that there's quite clearly defined planting seasons about when you can grow your crops. There are some commercial agricultural outfits in South Africa and in some of the other countries. Zimbabwe used to have very big commercial agriculture, so they would be able to do irrigation, but most of it's subsistence agriculture and small scale, so it depends on the rain. And these rains typically have been fairly dependable. There's some years when they don't come as strongly, but what we've already started to observe is periods when the rains fail altogether or come much later. So
is this a big problem then for farmers in Southern Africa, because it's really difficult to predict? We'll come on to the future of the climate in a bit, but it's difficult to predict basically because it's so inconsistent.
Yeah, it's you know when the rains should start, but that doesn't mean that they would start then. It turns out that in the present climate there's something called El Nino, so temperatures getting much warmer in the Pacific Ocean than they normally are. And it's quite clear that there's a strong link between, so if you had 10 El Nino events, seven of them would lead to drying over Southern Africa and wetting over East Africa, and the other 3 might not.
Right.
That's a pretty good hit rate. It means that if an El Nino is forecast to develop months ahead, which you can predict for El Nino, governments can start to put in place measures to assist farmers if those rains do fail.
Brilliant. Yeah, so that was the next thing I was going to come on to. El Nino. First, if you could just describe quickly what El Nino is, and then we can talk about how it particularly affects Southern Africa.
So probably the easiest way is to imagine that the Pacific Ocean is like a massive bathtub, and there's really strong winds that blow from South America towards Indonesia, and these winds are so strong that they move all the warm water to Indonesia, and every 2 to 8 years the winds get lazy and the water sloshes back across towards South America, and it makes the whole ocean far warmer than it typically would be because you don't have the winds to move the water and cool things down. That causes global changes to climates all over the world, and some really big impacts are felt where Southern Africa gets drier conditions and East Africa has wetter than normal conditions.
So you get things like flooding in Eastern Africa, and then droughts in South
Exactly.
Africa. And then what are some of the drivers? This is quite a loaded question, a big area of research. So what are some of the drivers for this El Nino?
Well, the first driver really is that the system is currently inherently unstable to this type of fluctuation. So these types of fluctuations have been happening for hundreds, thousands of years, and it's a type of thing that causes famine, has caused famine for many centuries. In terms of whether we are able to modify El Nino frequency, yeah, it's a huge area of active research.
Because there's some research that suggests that the frequency and intensity of El Nino is increased under human impact because of our CO2.
Yeah, I mean, what's useful to recognize in climate science is that there's some things which we have a lot of uncertainty about, and there's other things that we're much clearer about. And in the case of El Nino impacts, well, we know that the world is already warmer than it has been before, and it's projected to get warmer, and how warm it gets depends on how much carbon we're going to emit. And that means that for a standard El Nino event, when there is that drought, it's going to be that much hotter. So we might not be able to say something conclusively about El Nino, but we can say something conclusively about the fact that when those droughts come, they're going to be more severe because there's going to be more heat.
So it's very difficult for us to prove a causal link between human actions and El Nino, the frequency and intensity. But when they do happen, they're a lot worse, basically.
And that is due to anthropogenic warming. That kind of it turns up the dial on how bad it is.
Because of the high temperatures.
Yeah.
That's interesting. Let's talk about drought for a bit. The periods of drought are expected to be increased under climate change.
Yeah, so it's kind of a multi-scale problem. During a season, there'll be periods when there isn't rain. So it'll be the rainy season, and it can be dry for a week or 10 days. And actually, during certain parts of the life cycle of certain crops, that's important. So maize needs some good rains to get the seeds to germinate. But once it started growing well, it actually likes to have a period where there's lots of sun. There's still sufficient moisture in the soil, but it's not raining. It's really good for the growth. And then as it starts to fruit, so as it starts to make mealies, as they're called in South Africa, that's when it needs a bit of additional water, because those mealies are filling out each kernel of corn. What we know, which is a remarkable result because we see it across the world, is that dry spell length seems to be increasing. We've observed it already in some places, and it's certainly projected to happen. And if it increases, you can then end up with periods when there's no soil moisture left, and so crops can't grow. So that's a big concern. And that's kind of something about the character of the distribution of rain through the season changing. With regards to multi-year drought, so multi-year droughts,
longer term.
Yeah, so 3 consecutive years where the rains didn't come. Those are often associated with large-scale modes of climate variations, which we do modify with anthropogenic warming, but happen naturally anyway. And so it certainly seems that those multi-year droughts, maybe the frequency of the 3 or 5 year long drought might not change in the future, but as we said earlier, that drought under a warmer climate is going to be far more of an impact.
Far more worse. Okay, and then what about things the opposite end, flooding? So now precipitation.
Yeah, so again, it's this interesting thing that there's something in atmospheric science called the Clausius-Clapeyron relationship. It's a simple relation between how, as temperature increases, the atmosphere can hold more moisture, and that gives you a theoretical prediction of how much more intense the rainfall may become, because there's that much more water in the sponge, so to speak. And based on this, we predict an increase in rainfall. What we actually see is that in many parts of the world, already observed to today, there's been what's called a super Clausius-Clapeyron increase in rainfall. So it's exceeded that rate. So basically it says that for every so many degrees of warming, the rain rate will increase by this amount. And what happens is that for short duration, so rainfall of less than 3 hours, maybe even hourly rainfall totals, that relationship doesn't hold. There's actually, for every degree of warming, there's even more rain than falls than predicted by this.
So is it an exponential relationship?
No, it's not an exponential relationship, but it seems that the rate is increasing.
So you just get slightly more each time. So
and what happens then is you have the rainy season, which is projected to both have longer, hotter, dry spells, and then when it does rain, it rains more intensely. And so the likelihood of short duration flash floods seems to go up in the future. And that's something which there's quite a lot of confidence in that result, because it's something that people like Hayley Fowler at University of Newcastle, in collaboration with many other people around the world, has shown quite conclusively, and new climate models that are able to represent thunderstorms. Lizzie Kendon at the UK Met Office has done a lot of work on this, shows this happening in the future. So we both have observations showing it and climate projections showing the same type of thing.
But so we talked about drought, we talked about flooding and increased precipitation. To get a bit more physicsy, what are some of the drivers from a physical perspective? What just to help us understand, what causes this from a physical science perspective?
So the temperature goes up because there's more anthropogenic, because there's more greenhouse gas, which
greenhouse effects.
we were able to show is an anthropogenic source for that increase in that concentration. Because you have more moisture, because you have more temperature, the atmosphere is warmer, its ability to hold moisture has increased. And you already see that in the present day. If you were to go to the tropics, so you were to go to the middle of the Congo rainforest and fly in a drone, a kilometer above the rainforest, you'd find that it's really full of moisture. It's a very damp atmosphere.
Probably quite unpleasant.
But then if you were to go to somewhere else where it's cold, so if you were to go and do the same thing in Antarctica, you would find that it's a very dry atmosphere. It's so cold that it can hold very little moisture. Now, ask the question, where are the world's biggest thunderstorms? Well, they're not in Antarctica, rather. They're in the tropics. And that's because there is so much moisture in the air. And so, from the very first order of things, you increase the temperature, therefore you increase air's capacity to hold water, and therefore you increase, or you change the dynamics of these thunderstorms. You basically give them more energy.
So it's the ability to hold more moisture that is a big driver of this.
And then what happens is it turns out that in that type of atmosphere, what we seem to see is that the mode of releasing that energy is to have very rapid, sharp, and intense thunderstorms, as opposed to releasing the energy gradually.
Models and predictions. This is your area of research. In terms of the accuracy of these predictions, how can we be sure in terms of the validity of you mentioned that the one for the rainfall, to predict the amount of rainfall, how can we be sure of these predictions?
So there's a long history of making models which can represent the way the atmosphere flows as a fluid. So this is using something called Navier-Stokes equation on a rotating sphere, to be more technical, because Earth spins, and how and the thermodynamics of how air rises in the presence of moisture. So this is these thunderstorms, and they've coupled these together to make quite detailed atmospheric models, which then also are coupled to the ocean. These models have got more and more complicated and included more and more of the real world processes, and now we have about 40 of these models that make projections of what's going to happen in the future. There's many sources of uncertainty with these, and perhaps one of the biggest is actually what the carbon dioxide concentrations will be and other gases 50 years from now. We don't know that because we don't know what decisions we're going to make. But those 40 models then give us all plausible estimates of what the future world might look like. And what we do in our research group is try and understand what are the processes that those models simulate to be happening in a particular part of the world. So in this case, Southern Africa. And then we were able to compare that with observations of how those processes operate in the present day. Okay, and so something that you could, for example, focus on is the fact that a lot of that sharp gradient between the desert against the Namibian coast and the very high rainfall against the Mozambican coast and eastern Southern Africa, that gradient is maintained by these big bands of cloud which connect the Congo, the thunderstorms over the Congo, all the way to thunderstorms out in the Southern Ocean. So these are called tropical-extratropical cloud bands. What we can do is study, well, how many of these do we observe to happen every year? Do the climate models produce a similar number in their simulations? And then we can understand, well, what do the climate models say about the future of how many of these events will happen every month in 2050? And what comes out of that work is that there can be quite a variation in what that might mean, but for example, they all agree on the fact that there's going to be fewer of them.
Right. I just thought of a really interesting potential application in terms of predictions. What about AI or machine learning? What could we use that for?
Yeah, so the thing that AI is, machine learning, to be fair, most of it's machine learning, because artificial intelligence rarely speaks to something called general artificial intelligence, which is not what we're talking about. Machine learning, those methods have been used in climate science for decades, as they're higher order statistical methods with which to better understand those processes. And so actually, as part of my PhD research, I developed a method based on computer vision tools to identify these cloud bands that we've just spoken about.
Wow.
And it's a very simple method, but it kind of falls within the field of machine learning tools. It's a way of pulling patterns out of the data. In terms of going forward, the thing that machine learning is being used most effectively to try and deal with is that we run these climate models. They have very big, they break the surface of Earth into pixels, and then they simulate those pixels. But that gives you quite a grainy picture of Earth. And it's so grainy that basically they have maybe 10 boxes over the Congo rainforest. But the Congo rainforest might be having 30 or 40 or 200 thunderstorms at any one time. So there's only 10 boxes. You're not representing individual thunderstorms. You need to create a parameterization to guess what the effect is of the 20 thunderstorms inside your box.
Right.
Those parameterizations have proved very difficult to get right. We've had some of the smartest minds for the last 4 decades trying to get those right. And it's possible that machine learning is going to be a way to improve those small-scale processes which we're struggling to represent. So the Navier-Stokes equation, which is this fluid equation we solve on the rotating sphere, that's not going to change. And there's no point in, it's been shown already that you can use machine learning to derive that equation given observations of Earth's motion. But we know that equation, so let's use it. What we don't know is very clearly how changes in that fluid flow over the Congo change the number of thunderstorms, and how the number of thunderstorms change the fluid flow.
Right.
So that parameterization, machine learning, is being used to try and see if it's going to give us new insights in that aspect.
So if we could just talk about the different scenarios at various levels of warming. Let's start with the best case, very unlikely, 1.5. What would the South African climate look like at 1.5 degrees?
It'll probably look like something very similar to what it currently looks like, because remember, we're already just over 1 degree.
Right.
So already there's been changes experienced there, and those will be turned up a little bit more. So the risk of dry years will be increased. Dry years come with low river flows, which reduces hydropower, so there's less electricity, and for example, Malawi and Zambia are both very dependent on hydropower. If you've got no electricity, it's very difficult to run a good economy. And so in a way it'll be like what it's like now, but maybe a little bit worse. As you ramp up to 2 degrees, you start to get closer and closer to a situation of complete regime shifts where, it's okay to grow maize where I'm living now. In a 1.5 degree world, it's difficult to grow maize where I'm living now. But in a 2 degree world, I can't grow maize anymore. And in a 2 degree world, the question is, well, can I grow something else? And maybe I can grow sorghum, but maybe not even. And so, those types of risks come in. And those are amplified on top of African cities, which are urbanizing at a rapid rate as it is. It comes on top of land use changes, deforestation, and these types of things, which are also causing local effects. So it's really a case of things like COP reaching agreements on reducing global greenhouse gas emissions has a very real effect on the future generations of people that are trying to live subsistence lifestyles through most of Southern Africa.
Brilliant. And then just a final question, just to wrap it up. If you could just summarise, some of the greatest threats to Southern Africa, and then try and relate it back to the students here that will be listening, about why they should be most concerned and interested in this topic.
Greatest threats? Do you mean like generally, or?
Yeah, but specific to Southern Africa.
Yeah. I think we've spoken about a lot of them. I think the exposure to these climate risks is unhelpful. Generally, the regional economies as well are actually really dependent on what happens in the global economy. So, for example, South Africa now had its 3rd quarter of very low growth or negative growth in GDP, and so it's technically in a recession. Coronavirus has now just happened. That's not going to help any of the Southern African economies. Zambia, the whole large part of that economy depends on exporting copper, and copper is used in the manufacturing processes in China, which creates, the things that we're doing the recording on now, that come, that we would then buy in England. So these global interconnected economies result in there being less money to spend for people on the ground, on top of the fact that then it's even more difficult to grow their own food. And if they're living in cities, they're not growing their own food, they're needing to buy food from somewhere, which means there needs to be these economies, urban economies, where there are wages to be earned and food to be bought. And so I guess it's a difficult thing.
Yeah. And then lastly, if you could just persuade, if you were persuading someone either in an undergraduate or just before they're about to come into undergraduate, about why climate change, why is it why get interested as a student?
Yeah, I mean, I think it's one of the most pressing challenges that's going to face society across the world for years to come. There's a lot of uncertainty that remains on regional changes in climate. So we've spoken about, quite broad brush of types of changes you can get in Southern Africa. But there's a lot of hard science that still needs to be done to do what we can say regionalize global climate change. No one lives in the global mean. They live in locations.
Exactly.
How can we turn that global mean and change of temperature into something that means something to someone's livelihood? But part of that as well is the fact that people's lives have cultural values, there's social aspects, spiritual value. All of these values are part of how people navigate their time on Earth. And that means that you can come with the perfect scientific answer, but it doesn't fit into someone's socio-cultural framework. And that's where we need social scientists that are figuring out how to help people adapt to the changes that are coming. And so, there's a lot of very hard problems to be solved here for people of many different backgrounds. I do it as an atmospheric physicist, but I've got many colleagues that wouldn't mention Navier-Stokes and they would run a mile. But
particularly in the geography department.
But then in the geography department you can be having conversations with people who know about Navier-Stokes but who wouldn't want to touch it, but know about the cultural values in a particular part of the world, and find ways in which these can work together to help improve the resilience of people's everyday lives.
Brilliant. Well, that's a nice place to end. So basically, whatever subject you do, if it's politics, social science, or all the way to the physics and mathematical models of the climate, you can get involved with climate research. Brilliant. That was it.
Thanks very much.
Thank you very much.